Welcome to iLectureOnline, and here we're going to do a series on circular motion involving Newton's second law. So here, our first example, we have a horizontal surface, so we're looking at a bird's eye view on top of a horizontal surface, a mass of 2 kilograms attached to a string, attached to the center of its circular motion, radius of 0.5 meters, and what is the tension in the string if the period, and of course I have a T here and a T there, they do that a lot in physics, it's used the same letters for different things. This means the period of one revolution is 0.2 seconds. What is the tension in the string in order to keep that in orbit? And remember, Newton's first law says that if there's nothing there to keep it from going straight, what it normally would like to do, you need some sort of force to change its direction, and that would then be called the centripetal force. And the centripetal force can be found by saying it's the mass times the velocity squared divided by the radius. We have the mass, we have the radius, we do not have the velocity. So now we have to figure out the velocity of this thing, realizing that every 0.2 seconds it makes one revolution, or 5 revolutions per second. So for that we can say that distance is equal to velocity times time, or velocity is equal to distance divided by time. In the case of a circular path, the distance would be the circumference, 2 pi times the radius, divided by the time, which is the period. So that's how we find the velocity, which we'll then plug in here. Okay, 2 pi r, so that would be equal to 2 times pi times the radius of 0.5 meters, divided by the period of 0.2 seconds. All right. So how fast is that thing going around the circle? So we have 2 divided by 0.2 is 10, times 0.5 is 5. That would be 5 times pi equals 15 or 157, no, 15.7. Had a little trouble finding the decimal point on my calculator. So V is equal to 15.7 meters per second. All right, now that we know how fast it moves, we can plug that in there. And so this is equal to 2 kilograms times the velocity of 15.7 meters per second, quantity squared, divided by the radius of 0.5 meters. So let's square this number. Times 2 divided by 0.5 equals, and wow, quite a bit. That requires a force or a tension of 987 newtons. 987 newtons. So that's the force required to keep it going around a circular path, and that would then be known as the centripetal force. That's why the little c is there, F sub c, or centripetal force, 987 newtons. Sometimes it helps to look at a problem like this. Anytime something goes around a circle, we can think of two competing forces. So here's the object attached to a string, which causes a tension to be pulling inward to keep it in circular motion. And then we can think of this fictitious force called the centrifugal force, which always acts outward, F sub c, and I'll put little parentheses on there. So we call that the centrifugal force. That comes from the word centrifuge, and we know what we use centrifuges for. That's to take solutions in test tubes and causing them to push all the non-liquid materials to the outside of the tube, centrifuge. So our brain wraps itself around the idea that if things go around in a circle, they get pushed to the outside. So since we have that in our daily experiences, we can think of those two forces being equal, the tension pulling to the left and the centrifugal force pulling to the right. And if they are equal to each other, then things stay in a circular path. So centrifugal force would be the same as centripetal force, and the tension can be said equal to that. So tension equals to the centrifugal force, or the tension is equal to mv squared over r. So sometimes it helps our brain to wrap ourselves around the idea that when things go in a circle, there are two competing forces that are balanced so that things are kept in a circular path. When in reality what's going on is there a tension pulling on the object to prevent it from following Newton's first law, which means it wants to keep going in a straight path. To prevent it from doing that, the tension pulls it inward, and that tension is equal to the centripetal force mv squared over r. And that's how we like to look at circular motion.